Hi all, welcome back to Environmental Science 101. And last time out we were talking about matter and what makes up matter. Talked a little bit about simple chemistry, like what is an atom, what's it consist of, protons, neutrons, electrons. Um, Now we're kind of going to broaden out. We're going to move away from atoms and we're going to start talking about energy in general. And, in some cases, there are really kind of three ways to look at energy. Two of them, which I would say are very commonly examined and looked at by physicists and chemists, maybe molecular biologists, and that's really photons and electrons. Okay, so photons are little packets of light, and they have certain wave patterns. These different wave patterns have different types of energy, different amounts of energy, and we'll cover this here in a little bit. Okay, so that's one way to look at that. This energy is often considered free. It's coming from the sun. The planet is getting bombarded by photons all the time. Okay? When those photons hit our atmosphere, about 30% is reflected back. 70% is absorbed. Okay? And then what the atmosphere, what the planet does with that 70% really just determines what the atmosphere's makeup is, what gases are there. Okay? It depends on where those photons are hitting on the planet. What is the substrate? What is the rock mass? What plants are available? What is it blacktop? Is it sidewalks? Is it man-made objects? All these things determine what's going on with those photons. Okay, and then the next way to look at it is the electrons. Okay, so these photons themselves help to excite electrons in atoms. So this is energy that excites the electrons, and these electrons are typically from a perspective of chemistry perspective, they're going to be attracted to nuclei and other atoms potentially and form molecules. And when you get a bond between two atoms, we often consider that chemical energy or bond energy. Okay? And that's based on the electrons and the pull of the electrons and the energy that's involved with them. Okay? And then the last kind of way to look at energy is more from an organismal, more from things that are alive, and the energy that living organisms utilize. And really, to tell you the truth, it involves both of these in a great deal. Okay? And that is adenosine triphosphate, or what we call ATP. Okay, so it looks like this large molecule. Again, remember, molecules are just atoms bound together. So you got nitrogen bound to carbon, oxygen, hydrogen, phosphates, or phosphorus, and all kinds of things bound together here. All these bonds are chemical energy. Okay, but in order for this to form, we have to use this in conjunction with this, and we have specialized processes to make this. Okay, and that's that connection between all three ways to look at energy. Okay, so when we often talk about energy, it depends on what context you're talking about it. Are you talking about biological energy you are utilizing as a living organism that you consume and convert? Okay, then we're talking typically about adenosine triphosphate. Are we talking about energy that is running solar panels or heating the planet or driving the formation of ATP? Then we might be talking about photons and even electrons. Okay? So energy in general can be looked at in many different forms, and we'll come back and talk about that here in a second. But I want to share a couple quotes and a couple statements that have been put out there that, this one, more than 1,000 billion photons of light strike the tip of a needle every second. Of course, unless that needle is, tucked away and photons can't hit it. But the idea that some people have claimed, well, if we put all these solar panels out on the planet, that we're going to use up all the energy from the sun, and we won't have any energy from the sun to heat the planet or anything like that. We'll use all the energy from the sun. It's just not true. Okay? In fact, like the plants that occur on the planet only use about 1 to 2% of the energy that hit the planet to do photosynthesis. So the energy can definitely be utilized by solar panels and whatnot without affecting the sun. And the sun itself is sending the energy out to begin with. So, but just think about that. More than 1,000 billion photons, little packets of energy, are hitting the very tip of a needle every second. Okay? It's a huge amount of energy that is potential to do work. Okay? Thomas Edison, most famously known for the incandescent light bulb that he invented, or is at least credited with inventing. He said in 1930s that he'd put his money on sun. He'd put his money on solar energy, and that he hopes that we'll convert our energy sources to solar before we run out of oil and coal. Okay? And so he knew from a long time, as an individual that's dealing with electricity, as an individual that's designing light bulbs that replace candles in your house, okay? This individual realized at the time that digging coal and oil out of the ground to utilize it for electricity was a poor idea. That we should be capturing solar energy and using it to drive work. Okay? All right, so photosynthesis itself, it requires two really classes of energy. We kind of already talked about them before. Okay, we're going to hit them again. Okay. It requires potential energy, stored energy. Okay? That stored energy comes in often in chemical form, okay, in molecules, okay, atoms that are bound together. They're bonded together. When you break them apart, energy is released. Okay? And so potential energy is the stored energy. So you can think of it as like a dam. Okay? If we shut off all these gates, all that water back there is potential energy. Okay? When you open those gates, now due to gravity and the pressure that's flowing from being fed by maybe a river, okay, that water is rushing out. That is going to be kinetic energy, or the energy in motion. Okay? So you have two main sources of energy. You have potential energy and kinetic energy. You think of potential energy as the stored energy, and kinetic energy is the energy once it's been released and is able to flow and create motion, okay, or generate motion. Okay. So from a dam perspective, it's a pretty good example, but we can do another example. Okay, so example of that connection between potential energy, kinetic energy. Okay? So if you're a cyclist and you're on top of a mountain and you're just stationary and you're not moving, okay, that's potential energy. When you go down the mountain, and you're going to be releasing energy, okay? Not only from pedaling, but also from gravity and friction, speed, etc. Is going to be releasing energy. That energy being released is kinetic energy. Riding up the mountain, you're still releasing kinetic energy. The potential energy is the energy that's inside your body in the form of carbohydrates, proteins, lipids, some nucleic acids, and you're breaking those down through the process of cellular respiration and generating ATP so you can pedal the bike up the hill. Okay? So the potential energy is being broken to form kinetic energy. Okay? All right, let's drop back into talking about sun and talking about the photons and the energy that's coming from the sun. Again, it's coming in as wave patterns or wave, and the wavelength determines kind of the amount of energy that photon, that particle is going to pack. Okay, so things that typically have really small, short wave patterns will have high energy levels, and things that have really long or wide wave patterns will have less energy. Okay, so things like radio waves, there's not much energy in radio waves. So there's not very much energy in radio waves. It does allow them to travel a long ways, but they don't pack much energy. Microwaves, not very much either. We'll talk about microwaves in a second. Okay, and then you start getting into the spectrum, which we might call the biological spectrum. Okay, and that's infrared, visible light, and ultraviolet. Okay, these wavelengths here in this range from about 250 to 300 nanometers all the way to about 800 nanometers. Those are important for the perspective of most of life. Okay, the visible wave patterns are the ones that we can see, like our eyes have developed to see them. But other organisms can indicate or detect infrared. Some can detect ultraviolet, and many organisms, plants, will use wave patterns or wavelengths in this range in order to drive work and form bond energy, form that chemical bond. Okay, and then we know, of course, the X-ray and gamma rays, they're important for life as humans. They're important for our manipulations and our ways at which we can kind of change the planet through using X-rays to take pictures of the inside of people's bodies, to X-ray lots of different things, fossils, all kinds of things that we can use different X-rays for. We can also use some of these in order to treat foods and other things. But regardless of that, that's kind of the electromagnetic radiation that's coming from the sun that travels to the planet every second of every single day. Okay? So if we look at something like the microwave, okay, again, microwaves, it's not a strong wave pattern, but it travels a long ways. And so that's why microwaves are built with kind of a metal mesh. So if you look at your microwave when you get home and you look at the window, you can still see the visible light, okay, because visible light is also generated by a microwave. Okay, you can't physically detect microwaves, but they're there, and the microwaves themselves are blocked by that metal mesh. Okay? And so that metal mesh allows you to see the object that you're cooking, but not be affected by the microwaves themselves. Okay? And so again, this is just our ability, okay, humans' ability to take energy from different sources. Okay, in this case, most microwaves are ran off of electricity that is generated. Unfortunately, on this planet right now, most of it's generated via fossil fuels. So we're taking ancient energy and we're converting it into microwaves and visible light waves in order to cook a piece of pizza. Okay? But those wave patterns are constantly coming to the planet anyways. And I'm not saying that we should make little microwave boxes collecting the microwaves, but if you can make ways at which you can trap the energy that's coming in and utilize it to power energy in this box to cook your food, then that's probably better than digging up ancient fuel sources. Okay. Now let's talk about the wavelengths that are important again for kind of life on this planet. I'm not taking away from the other wave patterns, but these are the wave patterns that really drive life on the planet. Ultraviolet, okay, again, it can be damaging. It can cause skin cancer. It can cause what we call thymine dimers when DNA binds to itself on each side. That's caused by ultraviolet exposure. Visible light range, okay, this is what our eyes can detect. We'll talk about kind of eye development and things like that a little bit later when we talk about the connection between ultraviolet and infrared. And infrared is a heat energy that some organisms can sense. Okay, but when we look at it, again, this is a fairly small section of all the wave patterns that are coming in, but it's important for life on this planet. Infrared, again, is heat energy. Okay, some organisms take advantage of this and can sense the heat of other organisms, say things like pit vipers or like snakes that can sense the heat, the infrared that's giving off. There's some insects that can sense infrared. But heat energy itself is what's maintained and maintaining some of the heat on this planet. Visible light, okay, we already kind of talked about that and its role in photosynthesis. We'll come back. We'll talk a lot more about photosynthesis here in a little bit. And then ultraviolet. Ultraviolet has lots of things. Often it gets a negative kind of exposure or negative connotation, but ultraviolet is really, really important for many things. For organisms that can detect ultraviolet outside of the visible light range. Okay, lots of insects find flowers based on ultraviolet patterns. Ultraviolet wavelengths are really important for photosynthesis. Okay, just ask many plant growers. You can grow plants much quicker under ultraviolet than you can under visual light or visible light. So there's lots of reasons why we often in environmental science or science that's based on life on this planet, we talk about these three spectrums, these three portions of the electromagnetic spectrum. Okay. So that brings me to wavelengths. Really quick, if you're not familiar with why we see color, at least why humans see the colors we do, color is what is being reflected by an object. It's what's not being absorbed. Okay, so if you can, if you're looking at this kind of spectrum here and you're seeing green here, that's because that wave pattern, okay, is being reflected back. All the other wave patterns are being absorbed at this spot, but at 550 or so nanometers, that wave pattern is being reflected back. You're seeing violet, okay, at 390, everything's being absorbed except for 390. Okay, and so that's why we see color. Why do we see these three main colors? Okay, yeah. So sorry, red, yellow, and blue. Okay, are the three main colors, and then all the other colors are wave patterns that are related to it. The reason why we see three main colors is because we're what we call trichromatic. Okay? We have the ability to see those three colors. We have three color receptors in our cones, and so rods detect. So your eyes consist of rods and cones. Rods detect patterns of kind of black and white, so gray, black, white, and so they're detecting shadows and light. Lots and lots of organisms have the ability to detect shadows and changes in light. Okay, almost every organism with a light sensing organ have rods. Cones, on the other hand, are for being able to distinguish different wave patterns. Okay? And we have three different wave patterns that we can distinguish. And so all of our colors that we can distinguish, I think it's like 2,000 different colors we can distinguish. Although being a guy, I often say things like, rose is not a color, it's a flower. But, if you're looking at all the potential colors that we can distinguish, the human eye can distinguish about 2,000 different variations of color, because we have three types of cones, or three cones that can pick up these different colors. There are other organisms such as things like mantis shrimp that are deca or even higher chromatic. Okay, so there are 10 different wave patterns that they can see. So they see way more portions of visible light. They can also detect ultraviolet and infrared rays. Okay? And so, but the ability to detect different patterns of light has to do with, do you have the receptors that when this is reflected, when this 550 nanometers is reflected back, do you have something that absorbs it and can project it and have the neural connection that allows for you to say that's green? Okay? Some organisms do, some don't. Okay, but that's why we see color. Plants, leaves change color mainly because as a plant goes through the process of, or the seasons, and temperatures typically cool, different molecules, pigment molecules, okay, that absorb different light patterns. Okay, so things like chlorophyll A and B and keratins, carotenoids, xenophils, all these other pigments, they absorb different patterns. They absorb different wavelengths. Okay, and as the tree moves from summer to typically fall, or as the tree's in some cases dying, and they have less energy to remake things like chlorophyll. Chlorophyll reflects green, and that's why most plant leaves are green. Okay, but as they progress through the season, chlorophyll molecules tend to decrease, die out, and are not replenished, and things like carotenoids, the keratins, the yellows and the oranges, the xenophils, which are yellow, tend to increase, and then the keratins, which are orange and red, increase after that, or are present after that. I shouldn't say they increase. Okay, so when molecules die or deteriorate, chlorophyll goes first, and then the xenophils, typically in a plant leaf, if they have chlorophyll, xenophils, and keratins, chlorophylls go first, so the green goes away, you're left with the yellow, then the yellow goes away, and you're left with orange or red, okay, and then the red goes away, and you're left with brown, or a signal of death. Okay, so that's why kind of the leaves change color, that pattern of changing leaves. We can come back and talk more about this if you want to get really deep into this. We can discuss it, but it's important from a environmental science perspective, because if things are changing color earlier in season due to climate change, then often it's a sign that temperatures are changing, water might be reduced, and these organisms, chlorophyll, are not able to be established for a long period of time. If they're not changing till later in the season, maybe the growing season is extending, okay, and these plants are storing more sugars and things like that, and they're doing well later into the season. Okay, so there's lots of ways at which changing leaf color can indicate a change in the environment, and we can talk about that, and we will talk about that in more detail later on. Okay, next time we're going to dive into photosynthesis, okay, and look at the process of photosynthesis and how plants go about taking that free energy, photons, chemical energy, and forming stored energy, so organisms like us, which are heterotrophs, not autotrophs, we have to eat organisms to get our energy. And so organisms like us can exist on this planet. All right, next time.